Hello to everybody. Welcome to my presentation. My name is Shаяhan Haja-Beker. I'm running a learning lab project in Germany. The study I am presenting here is one of the case studies from this learning lab. In this learning lab, I use dynamic geometry. This is the overview. I will be talking a couple of minutes what is the theoretical framework, and mostly I will be talking about the case study. So problem area, it's technology, how we can help the pre-service teachers to use technology. Technology here, I mean the dynamic geometry. So this is the problem area and focus. Why do we have to conduct this study? I use a theoretical framework here called artifact-centric activity theory. It's originated from Germany. Actually, it belongs to the third generations of activity theory. It's a little bit variations. The main thing is that this is the artifact-centric activity theory. Subject, artifact being the middle, and then object, rules, and G refers to group. So from the literature, I learned that the theoretical framework supporting the instrumental orchestration, it's not enough because it's lacking here the psychological and sociological development of teachers. So that's why I decided to use one more theoretical framework. That's the artifact-centric activity theory. I will be using the acronym ACAT. Okay. Let's get into the terms that I will be using in this theoretical framework. I use the word instrumental orchestration. So I have to define what does it mean, instrument. Instrument is artifact plus a scheme to use the artifact. And then here the instrumental, this is how I define here. Instrumentation is the process through which the constraints and the potentialities of an artifact permanently condition the action of your subject in order to solve a given problem. This is the definition provided by Troche, a French mathematics educator. Here, instrumental genesis, this is the thing that here subject, and the interaction between subject and artifact. There are two processes involved here, instrumentation and instrumentalization. Here I use the word instrumental orchestration here. In the similar way, a musician will be orchestrating many instrumental music instruments. But in this setup, instrumental orchestration, I mean here the pre-service teacher is trying to use many digital tools in order to produce a harmony. That's the way I interpret instrumental orchestration in this technology-based teaching learning process. And I also use, how do I interpret instrumental orchestration? It is driven by the explanations given by Trivier. That is the didactical configuration by a pre-service teacher, an exploitation mode, and the didactical performance of the pre-service teacher. I will show you shortly the types of orchestrations according to Trivier. It has a lot of things, but I will be using an eclectic things. For example, spot and show, work and walk by the pre-service teachers and so many things here. Yeah. The research questions here. How did the pre-service teacher orchestrate her chosen instruments in a dynamic geometry teaching learning classroom? And how does the ACAD framework, artifact-centric activity theory framework, support to interpret the pre-service teacher's orchestration of instruments from the perspective of her students' work? So this is how, these are the main questions that I use. And research design, as I said, this is a case study, a primary pre-service teacher, JS. The technology is the dynamic geometry, and I'm using GeoGebra. And actually, in the learning lab, we have more than, we also use other dynamic geometry softwares, but this study is using this pre-service teacher has chosen to use dynamic geometry, GeoGebra. She has conducted this instrumental orchestration with 17 grade 4 primary school children, and the children will be working individually. That means each child has a computer. So the study was conducted in 2008. Yeah. A few details about the primary pre-service teacher. She's doing her pre-service teacher education at the University of Saarland. She finds GeoGebra is clear to her, and she thinks it is more user-friendly because the choices this is her own choice. Yeah, and she commented positive and also the negative aspects of GeoGebra, why she has chosen this. Among the other things, she says that she can use it, the clarification of the learning content, animation is good with GeoGebra, and also she feels that the children can be overloaded because there are so many tools, and the children, maybe it is difficult for the children to use. Yeah. So that I have used many tools to collect data, observation, JS lesson plan, and I have also used a screen recording of the children's engagement with rotational geometry and questionnaire interview. Yeah. This is the first one here. She, at the beginning of the lesson, she used a static model, a physical manipulative, and then she uses this windmill animation. I just show you shortly here. Oops. Yeah. It doesn't work. So these are the tools of GeoGebra that she used in this lesson plan. Move mode, triangle construction, rotating the triangle through 90 degrees, and so on. And this one, slider animation, I was trying to use it here. Yeah. So this is how it works, the animation with the slider regulation. Yeah. So just to give you an idea of how the classroom looks like, as you see that each child gets a computer, and the pre-service teacher here is using a central screen and to show, and she is also using a personal laptop here at her desk, and the children will be working here. So, and she also asked one of the students to come here and explain. So this is how she conducted her instrumental orchestration. Yeah. So again, going back to the ACAD, that is the artifact-centric activity theory model, as you see that I am trying to here use this workbook with central screen there are different types of orchestration. So what I have observed, I'm trying to make it in a diagrammatic format. So the activity here is the rotation symmetry through 360-degree. I have showed you the animation. And the action here is rotating the triangle. Yeah. So I have not much time. So I will be the outcomes. I just stop with this task. These are the tasks. The tasks, and task 1 is easier for the children. They made it in 20 to 40 seconds on an average, and task 2 is a little bit complex, and task 4 and 5 are the most difficult part. And you see that they have done it in an average 2.5 to 3 minutes. So these are the things that she found. She found that it's a very pleasant teaching orchestration. Yeah. As I have also the reflections, and I just here show you the way what she is speaking in this video. She started with the goal of teaching the rotational symmetry, and at the end she achieved her goal, and that was it. And thank you very much for the opportunity, and I will be answering your questions if you have any at the end of the session. Thank you.
Thank you very much.
Hello, everyone. Thank you all for being here. I'm Mehtap Ozen-Kush from Middle East Technical University. I have just finished my PhD at Mathematics Education Department. I will report on our study, a case study from our larger project in which we investigate possible synergies between visual arts and mathematics, which is about recognition of geometric shapes in an art studio. I will give you an overview about the background of the study. There have been some studies about visual arts and mathematics, and this study is mostly focused on the effect of art integration on students' achievement in geometry or mathematics, or transfer of learning from art education to the geometry. However, there is a need for detailed information about how they design tasks on the basis of theoretical background, and how they found particular results, and how the transfer occurred. Supportively, Winner and her colleagues in OECD report discussed the popularization of arts and discussed methodological problems in these studies, and suggested to conduct systematic research with a theoretical base. We approached this problem by investigating spatial thinking processes, which is regarded as a concrete thinking processes between visual arts and mathematics. In the current study, we focused on students' recognition of geometric shapes as a part of the project, to make students, to investigate students' thinking and to make their thinking visible in art-related environment. Studio thinking framework was used, which is proposed in visual arts education. And we also made use of minimalist artworks, which is considered as which could be considered as a visual art context with explicit use of geometric shapes and forms. And in this regard, we investigate 7th grade students' recognition of geometric shapes in an art studio in which students are engaged in geometry-rich minimalist artwork through studio thinking. Let me explain briefly this framework. This framework was proposed at the Harvard Project Zero and described as thinking dispositions that teachers intend to teach in visual art studios. They identified 8 thinking dispositions: envision, observe, understand artwork, reflect, stretch and explore, develop crafts, engage and persist and express. In the current study, the highlighted thinking dispositions were dominantly used in the current study. And they also identified 3 structures of the studio. Firstly, demonstration, and the second one, students at work part, and the last one, critique part. These parts can be used interchangeably depending on the nature of task. We adapted these structures into our context, and as observing geometric art works individually and then with their friends. And then they were asked to create and copy artworks. And lastly, they were asked to describe and evaluate their own artworks and their friends' artworks. On the basis of this studio thinking framework, minimalist artworks and studies on visual spatial thinking, we designed 3 studio works. I will just explain them briefly. In the first artwork, students were asked to observe and identify geometric shapes in the artworks of minimalist artists. And then they were asked to create artwork through hiding shapes into other shapes, like these artworks. In the second artwork, students similarly were asked to identify shapes that they see in these artworks and to identify similarities and differences between these artworks. Then they were asked to, in the next part, they were asked to complete an artwork. They were asked to choose one of the V series, and then they asked to continue it as if just beginning of another artwork. In the last studio work, students were asked to copy artworks with different characteristics at 1:4 scale. Instrumental case study was employed to research this question. The art studio environment, including these studio works, was used as a tool to investigate students' thinking process. And participants of the study were 6th, 7th grade students in a public school, and the study was conducted in the art studio of this public school. Before the study, we conducted interviews to learn about students' experiences in visual arts and mathematics, to identify their characteristics, and to learn about their feelings and opinions of visual arts and mathematics. And then each studio work implemented, and after each studio work, interviews were conducted, and like this one. And lastly, interviews were conducted after the study to learn about their reflections about the current study. And the major data source of the study were stimulated recall interviews that were conducted after each studio work. And the next one is observation of video recordings, and the last one, documents of the studios. In these data sources, students' written explanations, verbal explanations, and gestures, order of actions, changes in their sketches were investigated and analyzed. In the current study, we did not use a specific theoretical framework, and the 2 studies on spatial thinking provided basis for our coding and adapted to the context of visual arts and mathematics, because these studies mostly were conducted on early child education and psychology domains. And findings of the study. The analysis of students' thinking indicated students were in the 4 major processes of recognizing shapes. The first one is students related geometric shapes with real-world objects. The second one was students identified geometric shapes and their properties. And third one is students identified shapes through disembedding and embedding. And lastly, students identified shapes from different orientations or viewpoints. I will explain them briefly. Some of the students related geometric shapes with real-world objects. When they were asked to identify shapes in the artworks, and they also related geometric shapes with real-world objects during creating artwork, as in the last example. Secondly, students identified 2D shapes and 2D representations of 3D shapes in the artworks. They also identified and reflected on their properties. They mostly focused on length relations of the shapes and number of the lengths. And while they were recognizing 3D shapes, they mostly focused on number of faces. However, they mostly had confusions about triangle pyramid and triangular prism, and identification of properties of pyramids. And thirdly, students identify shapes through disembedding and embedding. Students at first glance, when they were asked to observe artworks, they at first glance identified 2D shapes. After they observed the artworks with their friends, they became to realize new shapes and 3D shapes. Okay, and lastly, they also identified shapes from different orientations, 2D shapes from different orientations. They identified rectangles, squares, that are presented at different rotations. However, when some of the students identified triangles, similar triangles at different rotations with different names, such as equilateral triangle and right triangle. And they also identified three-dimensional shapes in the artworks from different viewpoints. Okay, and then lastly, this study made visible four major processes of recognizing shapes, and this study also provides clues about interwoven process of these ways of thinking. And lastly, this math art environment will have a potential on making students' thinking visible in the intersection of visual arts and mathematics. By using artist artworks, encouraging students to sketch and drawing and describe and critique artworks. Lastly, this as a final point, this study will be an initial step for further investigation of possible synergies between visual arts and mathematics. Thank you.
Good morning. My name is Ana Barbosa, and I work in the Polytechnic Institute of Viana do Castelo in Portugal. And I'm presenting this oral communication also in behalf of my colleague Isabel Val, that is also here at the conference. This is how we divided our presentation into 5 topics. I will not waste time here. So to contextualize, because we work in teacher training courses, it's important for us to engage future teachers in experiences that are close to the ones they are going to provide their own students in the future. So this study is developed in the scope of teacher training. Also, we have been experiencing some curricular changes in our country in terms of primary education, and these changes have been bringing some difficulties for teachers to highlight the meaningfulness of mathematics and also its inductive side. So we believe it's important to explore tasks and resources that highlight these aspects. In light of these ideas, we are presenting an exploratory study on an experience conducted with future teachers of primary education, analyzing their performance in identifying and constructing symmetries, especially friezes and rosettes, with different resources. Geometric transformations are a part of our school curriculum in primary education and are one of the most important applications of mathematics in daily life, allowing the establishment of rich connections, which helps bring meaning to mathematics. They also enable students to explore and create patterns, to solve problems and think spatially. And these are aspects that relate to inductive and visual approaches. Adding to that, students generally show a low level of learning when geometric transformations are concerned. So we think it's important to consider a variety of working contexts, one being the use of technology to mediate learning. In this study, we adopted a qualitative approach of exploratory nature. The participants were 14 future teachers of primary education in the context of a curricular unit of didactics of mathematics. Data was collected through observation, written productions, and photo records, and was analyzed in an holistic manner, focusing on students' performance and students' reactions. During the classes, we tried to understand how these future teachers reacted in different working contexts. First, they were exposed to a teaching model about geometric transformations and symmetries. Here they had to formally construct with drawing and measurement materials and identify and characterize these geometric elements in a paper and pencil environment. Then they used a Portuguese software that's called Jekla to search for symmetries, classify and generate friezes and rosettes. And finally, they had to construct artifacts, contacting firsthand with examples of a day-to-day use of these geometric elements. So in the paper and pencil environment, students did not present difficulties in the construction of friezes and rosettes. And besides the more formal constructions with drawing and measurement materials, they explored different representations of friezes and rosettes. We only see here the friezes. And even equivalent representations using manipulative materials as, for example, the pattern blocks. These are some examples of other tasks they performed. In general, they did not show difficulties in identifying friezes and rosettes. They were able to identify the motif in friezes and also the properties. And they identified symmetries in a rosette, reflection and rotational symmetries. In some cases, they revealed difficulties related to the identification of the angles in the rosettes. This is another task they performed. They found it to be more complex than the previous ones. We think it's because it's a less routinized task and it demands good visualization skills that some of them were lacking. Some of them presented wrong answers, as you can see in the bottom examples. And we think these students may benefit from some kind of manipulation, either with materials or other resources. Then they used a Portuguese software called Jekla. It also has an English version. This stands for generation and classification, hence the name, and they used 3 of the features of this program. Search for symmetries as a previous approach, with an intuitive perspective, and they explore the existence of translation, reflection, rotation, and glide reflection in a given image. Then they use the generator of rosettes and friezes, using an image of their choice as a starting point to select the motive. And they also selected, as we can see above, the type of symmetry they wish to represent. Finally, they proceeded to the classification of rosettes and friezes, and after doing the classification and the identification of the properties, the program presents a final report of the students' work as a feedback. So the students found the software to be very intuitive and pointed out the contribution of visualization to develop mental images about symmetries. They highlighted the importance of being able to test conjectures. Generally, they did not exhibit difficulties in identifying symmetries in the explored figures, nor in generating friezes and rosettes. A few of them revealed difficulties in classifying some types of friezes in certain figures. They valued the possibility of freely generating friezes and rosettes using a motive that they selected. In spite of valuing the potential of the software, in some cases, they felt the need to recur to paper and pencil to support their explorations. Finally, students had to construct and/or decorate artifacts like boxes, bookmarks, and cup holders. They come up with simple elements of decoration, especially in friezes. However, they understood that this is a current application of geometric transformations in daily life, and we think it's the reason they valued this experience. They had to write a report explaining formally the process that they use in decorating these artifacts, and here the results were diverse. These examples are from students that identified in a clear manner how they proceeded. They characterized the elements that they used and the transformations operated. However, in other cases, they presented some errors, like, for example, wrongly identifying the angles in a rosette, or others that did not explain at all how they had proceeded, showing only the final result, as we can see in the last figure. So to conclude, in the paper and pencil environment, the majority of them identified and applied symmetries with relative easiness. However, some difficulties were experienced in characterizing rotational symmetry in rosettes, and also in tasks demanding good visualization skills. In JECLA, they valued the main tools of the software and considered it to be very intuitive and an aid to construct mental images, but they also showed some difficulties in the classification of certain friezes. In the artifacts, they were engaged while they had to construct it. Some of them showed a weak aesthetic sense because they used whichever technique they wanted. They opted mainly for basic elements, both in friezes and rosettes, and a few students showed some difficulty in identifying the minimum motifs and the geometric transformations that generated some of the rosettes and friezes. So thank you for your attention.
There is training methods and ideas. as well as use of tools and method of experimental mathematics in the teaching of mathematics and geometry in particular, are modern topics both at school and the university. The aim of research work in the process of education is to provide the students acquisition of research skills as a way of exploitation of reality and developing the ability to research thinking and targeted cognition. It's known that experiment is the most important means of scientific knowledge. Many pedagogical studies have theoretically proved and experimentally confirmed that experimental research activity in education has a great developing potential. Students learn the information that have discovered independently better. There is different types of research tasks, and one of them we can see in the slide. Question is that teacher gives task. Procedure is it means that teacher help to organize study, and solution it means that a solution of task is known. Geometry possesses the greatest experimental potential among all branches of mathematics. Many geometric facts can be verified experimentally, and training can be carried out in the form of the study or research based on computer experiments. I teach geometry at Saratov State University, and I also teach computer geometry, in English maybe computational geometry. Scientific literature gives a lot of examples that illustrate the effectiveness of experimental method in solving a mathematical task. For example, we can see the simple task of analytic geometry. First level by Bunch and Bell, we can see in the slide. For example, now we moving the point M along the ellipse, we see that angles are straight. And then the students need to prove this statement, this proposition. And we can see many other tasks, simple tasks, for example, of analytic geometry. For example, another task. Student needs to visualize geodesic that goes from a given point in a given direction from a given rotation surface to foresee a dynamic change of point, direction, and length of the geodesic. Computer geometry plays an important role in preparation of bachelors and can also be regarded as a link between other mathematical disciplines included in the curriculum. My colleague and I we would like to give such task which when we solve this task, we not only use a computer to visualization or only for calculate. We would like to give such task that computer is a tool, and we can formulate hypotheses, and a computer help us to solve this task. And my colleague, my teacher of symplectic geometry, given task for student, and I help to organize the study with computer. From this slide and this slide is some conclusion. And of course, we can say about experiment theoretical gap. It should also be mentioned that there are a number of negative aspects in resources devoted to the use of interactive mathematical environment in the educational process. One of them is called experimental theoretical gap, which arises in students' mind. It occurs in the situation that students face the reduction of motivation for deductive evidence and decrease of interest in theoretical thought. That means that the use of computer thought and experiment in theoretic mathematics, both at school and university, requires thoughtful pedagogical analysis and research. The teacher also has to formulate research tasks so that the student's mental activity should not replace it by a computer. There is some reference, as I said, there are many studies about that. For example, I read article by Professor Margot Kondratyeva, and I'm glad to see you about this. There is some task in computer geometry when we use in our lessons. And thank you.
Okay, and now we do invite all presenters, please, up front so that we can have a discussion and questions. So we can just move those. Okay, is there any questions, please? People are thinking. Okay. I'm going to start while giving you a chance to think about different questions. So, and I guess it's maybe all of you can think about it. So we've seen your presentations and your research on using various geometry platforms in order to teach very different levels, from primary students to primary teachers to geometry at the college level. So, my question is, how important is the choice of platform for teaching geometry at different levels? And do you see that, can you explain the pedagogical approach in relation to choice of technology? Let me translate just to make sure that everyone... Okay, very good.
Yeah, it's a good question. I think that at the primary level, more importance is given to algebra or number, how to use the operations, arithmetical operations like subtraction, addition, but less importance is given to geometry. Personally, I feel that spatial thinking, visual ability is as important as the numerical ability for the small children. But the practical thing is that in a textbook, in a primary school textbook, 80% of the textbook is allotted to teaching arithmetic ability, and most of the teachers, they do not, either they don't have personally interested, they are not interested to teach geometry, or they don't have time. And plus this, along with the visual, physical manipulative, it is difficult for the practicing teachers to use the visual manipulatives. They themselves need a lot of training. So I decided to focus my theory to the emerging teachers. So at least they have some ideas and they can motivate the primary school children to learn geometry in a better way.
Okay. We believe that visualization is a very important ability for students to develop, mostly or mainly in the first years, and not only in geometry, but in all areas of mathematics. Visualization is a very important aid, and it contributes with a lot of intuitive strategies that students can use in a diversity of contexts, but in geometry is fundamental. I don't think we can fully understand geometric concepts if we don't insist on visualization skills. So we think it's important to diversify the working contexts, paper and pencil environments, the experience of constructing themselves, the geometric elements, but also explore manipulatives because they contribute with other experiences and also technology. And in the scope of technology, there are a lot of resources we can use. We saw today GeoGebra, so it's a possibility, for example, for symmetries. But in this case, we wanted to use something more elementary and something more intuitive. And this program in particular, it doesn't serve to explore constructions, but they incorporate previously shown images that students can explore in terms of the properties of symmetries and understand in an intuitive way by manipulating those images how reflection works and how translation works and glide reflection, etc. So the possibility of exploring and discussing and seeing with their own eyes the effects of those transformations are important to construct and accommodate mental images. They are going to be important in later years, and it's more difficult to develop those abilities later. So we must start from the primary years.
использовать.
I'd like to ask, how do you choose the technical means of visualizations for your classes? What is key for you to choose this technology or that technology? What is important for you while choosing between, there are maybe main parameters that you consider while choosing it? Thank you. I'm interested in variety of ages for kids, but I'm personally more interested in smaller children, preschool and elementary school. Mm-hmm.
I think the starting point for that choice must be the goals we want to achieve. What do we want to work with the students? What's the main goal? Because we have a lot of technological resources nowadays, and I think that's the difficulty, what to choose. And as compared, for example, with manipulatives, all of these resources have advantages and limitations. And especially working with future teachers, we have to discuss with them exactly that. What does this serve for? What's the utility? But also what advantages and what limitations does that specific technology have, so they can make the best choice for their students. There are a lot of simple things to use, like apps that we have available in the internet to work on a lot of mathematical concepts, not only geometry. But I think we need to know in geometry, what do you want to work with the students? What's the main goal? And inside of the scope of the range of technology we have about those topics in particular, we have to make a choice in terms of what's the characteristics of our students, what the resources we have in the school. Do you have computers for all? Do they have to work in groups? So the choice depends not only on the tool, but on the school conditions, the resources the teacher has. So that's a lot of variables I can think of. I don't know if I answered your question. I think it's important to think of the age, because I think not all the technology will be suitable for students a certain age. Maybe it's more suitable for the teacher to use and show something, like in GeoGebra, picking up a certain example and then exploring a whole wide range of other examples to generalize and discuss with them the properties. But if we want them to explore themselves, I think the autonomy, something that it's simple for them to quickly understand how it works, because the most important is not the technical part, I think, but what they take from that, what they can deduce, what they can discuss, and what they can visualize. And maybe with the smaller students, that would be an important variable, something that it's easy and intuitive to understand in terms of usability.
I think I would like to add one more parameter to what actually she explained. She, from the perspective of, also we would like to think about all the agents of in the field of education. For example, in Germany there is educational politics. the government have certain educational policies, and they would like to give these resources to the children, especially in the primary area. For example, interactive whiteboard, computer, tablets, iPads. One of the parameters I would say that apart from the teachers and the children, and also the parents, most of them, they have computers at home or laptop or iPad or handy. So it all comes from the educational policies, what the government like to give to the children. I think that's one important factor, parameter.
I want to thank you, all of you, for your presentation, and I want to ask something to the last presenter about the sense of the proof, the meaning of the proof shared between the students and the teacher. Because if the meaning of the proof is to convince someone, convince others about a statement that could be true or not, well, it is simple to say for a student, it's true because I am convinced by the use of technology. Otherwise, if the teacher shares the meaning of the proof with the students as something that has to be explained, the students have to explain why. It is not sufficient, the use of technology in this situation. And there is a push, a support in order to investigate more and to explain why from the students. So which is the sense of proof shared in your experience between the teacher and the students?
I'm going to translate it for Dr. Бухашева, so 1 second. So the question is, вопрос в том, что имеется в виду под словом «доказательство», потому что очень часто доказательство для студента означает, что я убежден в том, что это правда. Когда студент использует технологии, очень часто у него возникает мысль, да, я вижу, это правильно, я в это верю, и это является достаточным убеждением. Как вы объясняете вашим студентам, что значит доказать? Является это ли вопрос на ответе, почему это верно, это утверждение верно на основе экспериментов? Потому что в ситуации, когда студента просят объяснить, почему что-то верно, то возникает необходимость что-то объяснять сверх того, что мы видим в применении технологий компьютерных.
Скажу тоже по-русски. Да, хорошо. Я привела пример простых задач по аналитической геометрии, чтобы показать суть компьютерного эксперимента исследования.
I showed an example of a simple problem in geometry to demonstrate the essence of the computer experiment in geometry.
Что я веду этот предмет уже на старшем курсе и вообще веду у математиков, поэтому такой проблемы в моей практике пока не возникало. А доказательство, это в привычном смысле, что значит доказать, вообще решить задачу. Поэтому...
I teach upper level students geometry in mathematics in general, and by the time my students get to me, we don't have a problem of what is a proof and why do I have to prove. It becomes like a normal routine, normal expectation.
То есть здесь у нас, я скажу, компьютерная вообще программа — это промежуточный этап в решении задач. Он у нас не завершающий, и я именно об этом говорила. То есть именно так мы рассматриваем, потому что просто вычислить, нарисовать, я не рассматриваю, хотя это тоже хорошо, но меня сейчас интересует использование так компьютера, чтобы это был промежуточный этап, чтобы мы могли дальше выдвинуть гипотезу и решать в таком для старших курсов задач.
In my approach, I'm using computer as an intermediate step. The computer experiment is used as a part of the whole process. It's never the last step of the solution and problem. We make conjectures and we experiment, but then there is always that piece dealing with explanations and proof.
Да, ну и у нас просто есть уже такие исследования на русском языке, но, в общем-то, не на английском языке, где уже ученые используют даже, ну, допустим, на плоскости, но есть такие примеры, когда можно провести эксперимент, выдвинуть гипотезу и, ну, каких-нибудь там простых свойствах, а потом доказывать. То есть мы уже как бы можем пользоваться образцами научных работ.
And nowadays there is a sufficient number of research papers that focus on using computer for the experimentation and making conjectures that then could be proved and from a very even basic plain geometry. So, and we could use even those examples from research papers and work of our students.
Okay, I have a follow-up question. Working. Maybe a little remark that there is a wonderful book by late John Borwein, the person who wrote the book on experimental mathematics, where he has mostly at the level of university mathematics, lots of examples where conjecture can be formed using computer, and then there is a follow-up. And many of those conjectures don't even have a full explanation yet, but there is a great confidence in their their truth. But the question to maybe to everyone is, as we just discussed, that the purpose of the exploratory phase is to form a conjecture. What is the role in your projects of students being able to formulate this conjecture and somehow justify those conjectures, even in the early grades? That's the question. I don't know.
We only presented an experience conducted with our students in this undergraduate course for teacher education. So this was only with the purpose for them to contact with another resource, technological resource they can use with their future students, but also align with that perspective of more experimental approach where the younger students can explore for themselves and, for example, discover or deduce properties related to these geometrical transformations. It doesn't have the same features as, for example, GeoGebra, where we can see all the dynamic alterations on the figures, along with the lengths and the angles that vary. It has another perspective where they can move the images and see the line, and if it's a reflection line, and perceive that for the translation they have to use a vector, and what is this and what does it produce in the transformation. So it's like finding out what are the properties underneath this transformation. So I think what's really important is for them to explore and then discuss among them those findings, and try after that to formalize the properties instead of being the teacher to tell them this is the reflection, it has these properties, and now let's apply these findings. So we believe that knowledge is better acquired when they have the possibility to find out for themselves. So it's in this logic.
Okay, I can. Thank you for your questions. I can make a comment on the base of my research study. It is mostly based on visual shapes and forms. Students made some conjectures about the properties of shapes or how a shape, while doing the sketching, they imagined how a triangular shape could be rotated, as in the second studio work in my study. They firstly made conjectures, and then they used papers to discover how it is rotated. They first had the difficulty. Maybe students' mathematical ideas could be developed through use of like technology and materials. And at the first step, they had very difficulty by just imagination and sketching. It is very difficult to because they sometimes made wrong drawings, and they need to feedback how it should be and how can develop their mathematical ideas. And these maybe firstly students are, I agree with you, firstly asked to explore themselves and then move on to the more abstract ideas with technology use maybe, and get feedback about their drawings maybe. That's my opinion.
I'm using dynamic geometry since 2004. I have been working with different age groups, starting from primary and with prospective teachers. As she pointed out, there are tools like moving and loci, and these tools provide wonderful opportunity for the students, whoever it may be, young or middle age, and the users of dynamic geometry, they have wonderful opportunity to conjecture something. And it is essentially an explorative platform that I would say, that I can say from my experience. I have tried it with also with different nationalities in England and also in India, and now in Germany. So for sure, they have the opportunity to conjecture, and the dynamic tools help them to facilitate their proving process. And I would say that there are difference of opinion among the mathematics educators, that's whether it's a formal proof or not, that there are difference of opinion, but for sure, it gives an opportunity for the users to hypothesize something and testing their hypothesis, that I can confirm from my experience.
Can you tell, please, you work with the children, they are in groups, yes? They use the technologies in groups. What happens to their communicative activity? Do they work only by themselves as individually, or they have some communication activity among them?
This experience wasn't yet conducted with younger students, only with future teachers of that age group. We have some concerns also in terms of classroom management, not only in the use of the resource itself. So, as I said before, it also depends on the conditions they have in their own contexts, because unfortunately in Portugal, in terms of technology use, our schools, not all of our schools are well equipped and prepared. And so some teachers have a lot of difficulties implementing this type of activities. But what we believe it's adequate is for them to work in small groups and try to discuss among them and exchange ideas and try the conjectures that these programs allow for, and then engage in a whole classroom discussion. In terms of classroom management, That's basically what we work with our future teachers, our students. Normally these dynamics work. I think it's richer that they can work and explore in smaller groups than individually. I know that we have materials and resources that are more adequate to work individually because of the way we use it. But if we have the chance to work in small groups and promote rich discussions, it's the best way to progress in acquiring knowledge.
I just want to add one more point to what she already explained. In my learning lab, the children, some pre-service teachers, they work with, it depends actually on the logistics. Some schools have many computers and some they do not have. So it comes from the experimental situations. I do go there and as a silent observer, I observe without participating in their process, teaching learning process, just to have a feel of this instrumental orchestration. I could say that at the initial stage, when two children or more than two children working with one computer, there is, at the initial stage, there is some hiccups. One dominating child will be using the mouse and doing all the work, and the other is waiting for the opportunity to grab the mouse. And this things happens, as she already put it, the initial excitement got over and they really get into the problem, and these things will be gradually overwhelmed by the inquisitive, explorative attitude. I think to answer the question, the social interaction between the children, it is hard to generalize. In some, it depends on many factors, what kind of problem the children are working, and what is the classroom climate. It depends on many things, and it's hard to generalize. Individual work or group work, sometimes individual work is comes out to be better choice, and in some settings group work seems to be the optimal choice. So it's hard to generalize.